Okay guys, welcome to a new video. In the last video we calculated the generalized momenta for the particle moving in a potential VR described with spherical polar coordinates as is shown in the problem. So the problem says a particle of mass m moves in a central force field with potential V. So the Lagrangian is given, as we can see. We are going to find the Hamiltonian of the system, okay? Because in the last video we found, or we calculated, the momenta PR, p theta, and p phi. So for definition, or by definition, we know that the Hamiltonian is a function of the coordinates, in this case r, theta, and phi, and the generalized momenta, in this case PR, p theta, and p phi. So we are solving the part B of the problem, okay guys? So by definition, we have the Hamiltonian defined by this equation: the summation over the product of the generalized coordinate, okay, the derivative with respect to time, with the respective momenta, minus the Lagrangian of the system, okay? So in this case we have QE, QI, and PI are the generalized coordinate and momenta respectively, okay? The generalized coordinate and momentum, okay guys? So then we have that QI dot is equal to R dot, theta dot, and phi dot, and PI is PR, p theta, and p phi in this case. Well, we remember that from the last video. In the last video we calculated the generalized momenta, and we got the following equations: PR is equal to mass multiplying r theta. We got p theta equal to m r squared theta dot, and we got p theta, p phi, sorry, equal to m r squared sine square of theta phi dot. Alright, so what we are gonna do here is this: we are gonna clear the generalized coordinates, right? So we solve these equations for the generalized coordinates. That way we get the following. Here we clear r dot is equal to PR dividing the mass. Alright, what we did here is this term was multiplying, and we moved this term to this side of the equation, okay? And because it was multiplying, it goes to divide on the other side. And the same we do with p theta. We are gonna calculate theta dot would be equal to p theta dividing the mass r squared. Alright, we cleared theta dot. So the terms that were multiplying theta dot, we send those terms to the other side of the equation, and because they were originally multiplying, they go to divide on the other side. And the same we do with p phi. In this case, phi is gonna be equal to p phi equal to sorry, okay, oh no, sorry, I'm gonna erase this and I'm gonna write it down again. Phi dot is equal to p phi dividing m r squared sine square of theta. All right, so those are the generalized coordinates. Okay, guys, so both in terms of the temporal derivative. All right, so what we are gonna do is this. We are gonna call this equation, for example, equation number 1, equation number 2, and equation number 3. All right, we are gonna call the Hamiltonian. We wrote the Hamiltonian originally like this because this is the formula for the Hamiltonian, the highlighted one. So we are gonna replace number 1 equation, number 2 equation, and number 3 equation into the Hamiltonian. Okay, so we do this. If we remember that the Hamiltonian is given by the summation over the multiplication of the temporal derivative of the coordinates by the momentum minus the Lagrangian, and we come back here and we see the generalized coordinates, right? The temporal derivative of the generalized coordinates, and we do this. The summation over the coordinates would be r dot, right, pr. Okay, applying the formula, the summation over the product of the generalized coordinate with the momenta minus the Lagrangian plus theta dot p theta plus phi dot p phi minus the Lagrangian. That's the formula. Okay, well, we know in advance r dot, theta dot, and phi dot, so we replace these formulas or these equations into the Lagrangian. So r dot is, we get the Hamiltonian is r dot, but we know that r dot is pr dividing the mass. Okay, this is r dot, pr dividing the mass. Okay, the same with p theta. Theta dot is p theta dividing m r squared. So this would be the first term is r dot pr. Okay, this is r dot plus theta dot, but theta dot is p theta dividing the mass multiplying the radius square. So this would be p theta dividing the mass r square p theta plus p phi is the same. P phi is, sorry, phi dot is p phi dividing the mass r squared sine square of theta p phi minus the Lagrangian. Okay, minus the Lagrangian. All right. So we get, this is theta dot, and this is phi dot. Okay. So we get the Hamiltonian. Okay, we multiply PR times PR p theta times p theta. We distribute this multiplication here, PR multiplying PR, p theta multiplying p theta, and p phi multiplying p phi. So we get in this equation PR square dividing the mass, all right, plus p theta square dividing the mass multiplying r square plus p phi square dividing m r square sine square of theta minus the Lagrangian. All right. But the Lagrangian, what is the Lagrangian? The Lagrangian is done in the problem, is given. Okay? So the Lagrangian is given by the problem. And the Lagrangian is L equal to 1/2 of the mass, parentheses, r dot square plus r squared theta dot square plus r squared sine square of theta plus phi dot square minus the potential. All right. So what we are gonna do is this equation of the Lagrangian, we are gonna replace this equation into the Hamiltonian right here. All right. The Lagrangian we are gonna replace. That's what we are gonna do. So, but before doing that, we are gonna distribute the 1/2 of the mass into the terms multiplying in the parentheses. So before doing that, we distribute 1/2 of the mass to multiply into the parentheses, all right, by the terms that are confirming the first of the terms into the parentheses. So multiplying this, so we multiply the first term, we multiply the second term, first term, the second term, and the third term. All right, that way we get for the Lagrangian the following equation: L equal to m r dot square dividing 2 plus m r square theta dot square dividing 2 plus m r square phi dot sine square of theta phi dot square dividing 2 plus the potential. All right. Well, we know already. We know r dot, we know theta dot, and we know phi dot. All right, guys. So we know those terms. when we replace phi dot, theta dot, and r dot into the Lagrangian right here, r dot, theta dot, and phi dot, when we replace those terms into the Lagrangian, we remember that we calculated those terms. They are here, r dot, theta dot, and phi dot. We replace these number 1, 2, and 3 equations into the Lagrangian. We get m divided 2 multiplying r dot squared, but we know that r dot is pr dividing the mass. Alright, but because it's elevated to the second power, so we have to elevate to the second power the numerator and the denominator. So the same for the second term, the mass multiplying r squared dividing 2 multiplying theta dot squared, but we know that theta dot is p theta dividing the mass r squared, but because theta is square, we have to have the second power in the numerator and the denominator. So we get p theta squared dividing the mass squared multiplying r to the 4th power. Okay, and the same to the third term, m r squared sine square of theta dividing 2 multiplying p phi dividing m squared. Okay, r sine, give me a second please, sorry, phi dot, in this case, for example, this term is this. Okay, so multiplying phi dot, but phi dot is p phi dividing m r squared sine square of theta. Alright, but it's phi dot squared, so we have to have here p phi squared m squared r4 sine 4 of theta. Okay, plus the potential Vr. Alright guys, well, now we simplify the equation. So we simplify this mass with this mass square, the same here, mr squared with this term in the denominator, the same here, mass with mass, radius with radius. This is 4, this is 2, this is 4, this is 2, and this is 4. Alright, so we get L is equal to PR squared dividing the mass plus P theta squared dividing mr squared plus P phi squared dividing mr squared sine square of theta plus the potential. Okay, so this is the Lagrangian. In terms of the Lagrangian, in terms of the momentum of pi. Okay, p theta, pr, p theta, and p phi. This is the Lagrangian. So the next step is we know the Hamiltonian, okay? The Hamiltonian is this term here, right here, the Hamiltonian, and we can call this equation number 4. Okay, equation number 4, and we have this equation, and we call the Lagrangian number 5. Okay, guys, what we do is we replace 5 into 4. All right, we replace equation number 5 into equation number 4, and equation number 5 is PR squared dividing the mass h, then we get PR squared dividing the mass plus p theta squared dividing the mass r squared plus p phi squared dividing the mass r squared sine square of theta minus the Lagrangian. But remember the Lagrangian, what it is, minus the Lagrangian, but we calculated the Lagrangian, and it's right here, is number 5 equation. Okay, so I forgot to write something, sorry, I forgot to write a 2, 2, and 2. Okay, so it's 1/2 of PR squared dividing the mass, and for the other terms 1/2, 1/2, and 1/2. So we get PR squared dividing 2m plus p theta squared dividing mr squared plus p phi squared dividing 2m r squared sine square of theta. Okay, we write it like this, minus here is plus the potential BR. So the distribution of the sign, for example, here we have minus, and inside the bracket we have plus on the first term and plus for the potential. So when distribute the minus sign into the bracket, every sign is gonna change, right? Then we have the following equation: PR squared dividing the mass plus p theta squared dividing mr squared plus p phi squared dividing 2m r squared sine square of theta, well, minus, okay guys, minus, oh sorry, minus, I write in the next line because this is too short. I have enough room here to keep writing in the same lane. So minus, I distribute the terms, okay, the sign here, the minus here, and the term, the fourth, each term, okay. So we get minus PR dividing 2m minus p theta squared dividing mr squared plus p phi squared dividing 2m 2m r squared sine square of theta minus the potential. So this term is alike with this. This term is alike with this with this, and this with this. So this is PR squared dividing the mass minus 1/2 of PR squared dividing the mass plus P theta squared dividing MR squared minus 1/2 of P theta dividing MR squared plus P phi squared dividing MR squared sine squared of theta minus P phi squared minus 1/2 of P phi squared dividing MR squared sine squared of theta. So if we do the math, if we do the addition, we get, if we do the addition, or in this case is the subtraction of PR squared minus 1/2 of PR squared plus P theta squared minus 1/2 of P theta squared plus P phi squared minus 1/2 of P phi squared. So we get PR squared dividing 2m. Okay, this is the result of the subtraction of this term with this plus P theta squared dividing 2m r squared is the result of the subtraction of this with this, and P phi squared dividing 2m r squared sine squared of theta is the result of the subtraction of this with this minus the potential VR. And this is the Hamiltonian for this problem. And remember, the Hamiltonian is a function of what? If you remember, the Hamiltonian is done in terms of the momenta and the generalized coordinates. Okay guys, so this is the result of the problem. Hopefully it helps you to understand Hamiltonians and Hamiltonian physics. Okay, see you in the next video solving the next part of the problem. Bye. Don't forget to subscribe and to give me a like. If you can share, it would be wonderful. Okay guys, see you in the next video. Bye.